Today, I want to tell you about a man who completely changed how we understand reality, a scientist whose ideas made the invisible world visible and turned mystery into mathematics. His name is Erwin Schrödinger, and he was one of the founding fathers of quantum theory. Erwin Schrödinger was born on August 12, 1887, in Vienna, Austria, a city that at the time was one of the most important cultural and intellectual centers in Europe. His birth came at a time when the world of science was undergoing quiet preparation for a revolution that would soon change the way humanity understood nature. From his very early childhood, Schrödinger was surrounded by an environment that valued learning, curiosity, and deep thinking. His father, Rudolf Schrödinger, was a wealthy and intellectually curious man who owned a linoleum factory but had a deep passion for science. Rudolf was not a professional scientist, but he was a serious amateur who collected scientific instruments, books, and ideas, and he passed this love of knowledge on to his only son. Schrödinger's mother, Georgine Schrödinger, also played an important role in shaping his early mindset. She came from an academic background and had a strong appreciation for literature and culture. She made sure that young Erwin was introduced not only to scientific thinking, but also to poetry, philosophy, and classical literature. This balance between science and the humanities became a defining feature of Schrödinger's personality. He did not grow up as a narrow-minded scientist. Instead, he developed a broad intellectual curiosity that allowed him to think deeply about the nature of reality itself. During his early childhood, Schrödinger was taught at home by private tutors before entering formal schooling. He learned mathematics, physics, and classical languages at an early age. Unlike many children, he found joy in solving mathematical problems and understanding physical phenomena. He was fascinated by light, sound, and motion, and he often tried to imagine what the world looked like beyond what he could directly see. This imagination later became a powerful tool in his scientific work, as quantum physics often requires thought experiments and abstract thinking beyond everyday experience. As he entered secondary school, known as the Akademisches Gymnasium in Vienna, Schrödinger quickly distinguished himself as an exceptional student. He excelled in mathematics and physics, but also performed highly in literature and philosophy. He was deeply influenced by the scientific developments of the late 19th century, particularly classical mechanics and thermodynamics. At this stage, he admired scientists such as Newton, Maxwell, and Boltzmann, who had already laid much of the groundwork for modern physics. His teachers recognized his talent and encouraged him to pursue a career in science. One of the most important influences on his early education was Ludwig Boltzmann, a famous Austrian physicist who helped develop statistical mechanics. Although Schrödinger was young and not yet directly working under Boltzmann, he was inspired by Boltzmann's ideas and approach to physics. Boltzmann's tragic death in 1906 deeply affected the scientific community in Vienna, and it left a strong emotional impression on Schrödinger as a student, making him realize that science was not just about formulas, but about deep human struggle and passion for understanding the universe. In 1906, Schrödinger entered the University of Vienna, where he formally began his higher education in physics. He studied under some of the finest minds of his time, including Franz S. Exner and Friedrich Haesnerl. These professors shaped his rigorous approach to scientific thinking and experimental accuracy. University life exposed Schrödinger to advanced mathematical physics, electromagnetism, and classical theories of matter. At this time, quantum theory was still in its infancy, but strange new ideas about atoms and radiation were beginning to challenge traditional views of physics. As a university student, Schrödinger proved himself to be disciplined and intellectually fearless. He did not simply memorize theories, he questioned them. He asked why nature behaved in certain ways, and whether the existing theories truly explained reality or merely described it. This habit of questioning became one of his greatest strengths as a scientist. While many students were satisfied with learning what was already known, Schrödinger always felt drawn toward the unknown and unexplained. In 1910, Schrödinger completed his doctoral degree with a dissertation on the topic of advanced theoretical physics. His work showed a strong command of mathematics and physical intuition. After earning his doctorate, he began working as an assistant at the University of Vienna. This period allowed him to deepen his understanding of experimental and theoretical physics. He continued to explore difficult concepts such as heat conduction, optics, and the theory of colors. These early research experiences trained his mind to approach complex problems with patience and creativity. Soon after, the outbreak of World War I in 1914 interrupted his academic life. Schrödinger was drafted into the Austro-Hungarian army and served as an artillery officer. Although war was far removed from his love for science, this experience taught him discipline, resilience, and the harsh realities of the world. Even during the war, he tried to keep his connection to science alive by reading and thinking about physics whenever possible. The contrast between the destruction of war and the beauty of scientific discovery made a deep emotional impact on him and strengthened his desire to dedicate his life to peaceful intellectual work. After the war ended, Schrödinger returned to academic life with renewed determination. Europe was in a state of intellectual rebuilding, and science was moving quickly into new territories. He accepted teaching positions at several universities, including in Jena, Stuttgart, and Breslau. During this time, he refined his teaching skills and became known as a clear and inspiring lecturer. He had the rare ability to explain complex ideas in a simple and elegant way, which made him popular among students. His early teaching career also helped him develop confidence in his own thinking. By explaining difficult topics to others, he sharpened his own understanding. This period was crucial in preparing him mentally for the revolutionary work he would later perform in quantum mechanics. His background in both mathematics and classical physics gave him a strong foundation, and his philosophical mindset gave him the courage to think differently from most of his contemporaries. What truly made Schrödinger unique was the way his early life blended science and philosophy. He was not only interested in how things worked, but also why reality existed the way it did. He read the works of great philosophers and often reflected on the relationship between mind, matter, and the universe. This deep philosophical curiosity made him especially suited to contribute to quantum theory, a field that often challenges common sense and forces scientists to rethink the nature of existence itself. By the time Schrödinger reached his late 20s, all the pieces of his early life had come together. His family environment had nurtured his curiosity, his education had trained his mathematical and scientific skills, and his personal experiences had shaped his character and determination. Although he had not yet created his most famous work, the foundation for his future success was already firmly built. The curious child from Vienna was slowly becoming the brilliant mind who would soon change the world of physics forever. This early period of Erwin Schrödinger's life was not merely a preparation stage. It was the soil in which his later genius would grow. His love for learning, his courage to question established ideas, and his unique blend of scientific and philosophical thinking all began in these formative years. They shaped not only his career, but also the future of modern physics. As Erwin Schrödinger moved further into his academic life, his intellectual personality continued to mature in ways that would later define his revolutionary contributions to physics. After gaining valuable experience in teaching and research, he began to realize that physics was not just a profession for him, but a lifelong mission. The foundations laid during his childhood and university years started to show clear results as he developed a unique way of thinking that combined strict mathematical discipline with bold, imaginative insight. Schrödinger's early career was marked by constant movement between universities, which exposed him to a wide variety of scientific traditions and teaching styles. This mobility was not a weakness, but a strength. Each institution gave him a broader view of how science was practiced in different parts of Europe. He observed how different scientists approached problems, how they designed experiments, and how they taught complex material. These experiences slowly shaped his own scientific style, which later became famous for its clarity, elegance, and depth. During these years, Schrödinger also struggled with personal doubts and intellectual challenges. Like many great thinkers, he often questioned whether he was truly capable of making a significant contribution to science. There were moments of frustration when problems seemed unsolvable and the future felt uncertain. However, these struggles strengthened his mental discipline. Instead of giving up, he learned how to sit with difficult questions for long periods, turning them over in his mind until new perspectives emerged. This ability to remain patient in the face of confusion later became essential when he worked on quantum theory. He also spent a great deal of time reading the scientific literature of his time. He carefully studied the works of Max Planck, Albert Einstein, and Niels Bohr, absorbing their revolutionary ideas about energy, light, and atomic structure. Although he deeply respected their work, he did not see their theories as final answers. Instead, he treated them as stepping stones toward a deeper understanding of physical reality. His education was no longer limited to classrooms and textbooks. It became a lifelong self-driven journey of exploration. Another important part of Schrödinger's early intellectual development was his growing interest in the philosophical foundations of science. He felt that physics should not only describe how the world behaves, but should also try to explain what reality truly is. He read works of Eastern and Western philosophy, developing a belief that consciousness and the physical world might be more deeply connected than scientists usually admitted. This philosophical outlook later influenced the way he thought about quantum mechanics, where the role of the observer becomes a major theme. The post-war academic environment was difficult. Universities had limited resources, and many scientists were struggling to rebuild their careers. Despite these challenges, Schrödinger remained deeply committed to research and teaching. He believed that science was one of humanity's greatest tools for progress and understanding, especially after the destruction and chaos of war. This belief gave him a sense of purpose and moral responsibility. He did not just want to become famous. He wanted to contribute something meaningful to human knowledge. His teaching style during this period became one of his most admired qualities. Students described him as calm, thoughtful, and deeply engaging. He did not simply lecture while students listened silently. He encouraged discussion, curiosity, and critical thinking. He wanted his students to feel the same excitement about discovery that he felt himself. This made him not only a great scientist, but also a great educator who helped shape the next generation of thinkers. As Schrödinger approached the mid-1920s, his early education and experiences began to converge towards something much larger. The scientific world was struggling to understand the strange behavior of atoms. Classical physics could no longer explain why electrons did not simply crash into the nucleus, or why atoms emitted light in specific, discrete patterns. These unanswered questions created intellectual tension across the scientific community. For Schrödinger, this tension was not discouraging, it was inspiring. He felt drawn to these unresolved mysteries. Behind his calm and gentle personality was a mind that constantly searched for deeper patterns. He was not satisfied with surface-level explanations. He wanted mathematical beauty, conceptual clarity, and philosophical depth all at once. This made him different from many of his peers, who often focused mainly on calculations or experiments. Schrödinger valued intuition and elegance as much as technical accuracy. This combination of traits, developed throughout his early life and education, made him uniquely prepared to make a major breakthrough. During this time, Schrödinger also developed strong habits of solitary thinking. He enjoyed long walks, quiet reading, and moments of deep reflection. Many of his best ideas began as vague thoughts during these quiet moments. He would slowly refine them, test them mentally, and connect them to existing scientific knowledge. This habit of deep, focused contemplation was not accidental. It was built over years of disciplined study and intellectual curiosity. He also learned from failure. Not every idea he explored worked out, and not every calculation led to a clear result. But instead of being discouraged, he treated failure as part of the scientific process. Each mistake helped him understand the problem more clearly. This mindset was crucial when he later faced the enormous challenge of formulating a new mathematical framework for quantum mechanics. By the time Schrödinger reached his late 30s, he had become a scientist with a rare balance of qualities: strong mathematical skill, philosophical depth, patience, imagination, and humility. His early life and education had quietly shaped him into someone capable of thinking beyond the limits of conventional physics. Without these formative years, the revolutionary ideas of quantum wave mechanics might never have been born. Although the world did not yet fully recognize his genius at this stage, those who worked closely with him could sense that he was on the verge of something extraordinary. His lectures became more refined, his questions more daring, and his ideas more original. He was no longer just a student of physics. He was becoming a creator of new physics. In many ways, these early experiences were the invisible engine behind everything he would later accomplish. They gave him the tools, the mindset, and the courage to step into unknown territory. While history often focuses on great discoveries, it is important to remember that such breakthroughs are built on many years of quiet learning, personal struggle, and relentless curiosity. Schrödinger's early life and education were not simply a beginning. They were the foundation of a revolution in human understanding. As this phase of his life came to a close, Schrödinger stood at the edge of a scientific turning point. Everything he had learned, read, questioned, and imagined was about to be tested in one of the most dramatic transformations in the history of physics. The stage was set for the birth of wave mechanics and the dawn of a new era in science, and the journey that started in a small home in Vienna was about to change the world. The birth of wave mechanics stands as one of the most revolutionary moments in the history of science, and it is inseparably connected with the brilliant mind of Erwin Schrödinger. At the beginning of the 20th century, physics found itself in a deep crisis. The classical laws that had successfully explained the motion of planets, falling objects, and the flow of heat suddenly failed when scientists tried to understand what was happening inside atoms. The tiny world of electrons and energy did not behave according to the familiar rules of everyday life. This growing confusion created the perfect conditions for a scientific revolution. Before Schrödinger's breakthrough, several important discoveries had already shaken the foundations of classical physics. Max Planck had introduced the idea that energy comes in small, discrete packets called quanta. Albert Einstein explained the photoelectric effect by showing that light could behave like particles. Niels Bohr developed a model of the atom in which electrons moved in fixed orbits around the nucleus. While these ideas were groundbreaking, they were incomplete and often mathematically inconsistent. Many scientists felt that physics was becoming a patchwork of partial explanations rather than a unified theory. Schrödinger entered this scientific landscape with a unique mindset. He was deeply influenced by Louis de Broglie's bold proposal that particles such as electrons might also behave like waves. De Broglie suggested that matter has a wave, like nature, just as light has a particle, like nature. This idea fascinated Schrödinger because it offered a potential bridge between two seemingly opposite pictures of reality, particles and waves. He saw that if this idea could be mathematically formulated, it might finally bring order to the growing chaos in atomic physics. While working in Zurich in the mid-1920s, Schrödinger began to focus intensely on developing a mathematical framework that could describe these matter waves. He was not simply trying to modify existing theories. He was attempting to build an entirely new way of understanding motion at the atomic level. He spent countless hours working through complex mathematical equations, often struggling with the limits of known mathematics. This period of his life was marked by intense concentration, loneliness, and creative tension. Slowly, the idea of wave mechanics began to take shape in his mind. Instead of imagining electrons as tiny balls moving in fixed paths, he began to think of them as wave-like entities spread out in space. These waves did not represent physical vibrations like water waves or sound waves. Instead, they represented the probability of finding a particle in a particular location. This was a completely new way of thinking about reality. It suggested that at the most fundamental level, nature was not deterministic in the classical sense, but statistical and uncertain. In 1926, Schrödinger presented his most famous contribution to science, what is now known as wave mechanics. At the heart of this new framework was a powerful mathematical expression that would become one of the most important equations in physics. This equation did not give precise paths of particles. Instead, it described how the wave-like properties of particles evolved over time. With this single idea, Schrödinger gave scientists a powerful new tool to explore the atomic world. At first, many scientists were confused by wave mechanics. The idea that particles could behave like waves seemed strange and difficult to accept. Some physicists favored a different approach developed by Werner Heisenberg, known as matrix mechanics. For a short time, these two approaches appeared to be competing theories. However, it soon became clear that both methods were mathematically equivalent and described the same underlying reality in different ways. This realization strengthened the foundations of quantum mechanics and showed that Schrödinger's wave mechanics was not just a clever idea, but a true representation of nature's behavior. The development of wave mechanics was not only a scientific breakthrough, but also a philosophical turning point. It forced scientists and philosophers to rethink what it meant to describe reality. In classical physics, objects had definite positions and velocities at all times. In wave mechanics, these certainties disappeared. Instead, reality became a world of probabilities, waves of possibility, and outcomes that only became definite when measured. This shift had a profound impact on how humans understood the universe and their place within it. Schrödinger's personal experience during this period was a complex mix of excitement and inner struggle. He felt the thrill of discovering something fundamentally new, but he also experienced doubt. He questioned whether the scientific community would accept such a radical idea. He worried about whether his mathematics was truly correct, and whether his interpretation would stand the test of time. These doubts did not weaken him. They pushed him to refine his work further and to present it with clarity and precision. As wave mechanics gained attention, experimental evidence began to support its predictions. Phenomena such as electron diffraction, where electrons produced interference patterns similar to light waves, provided powerful confirmation that matter really did have wave-like properties. These experiments transformed wave mechanics from a bold theoretical proposal into an accepted scientific reality. Schrödinger's ideas were no longer just mathematical dreams. They had become experimentally verified truths about the nature of matter. The birth of wave mechanics also marked a turning point in scientific collaboration and communication. Scientists across Europe and beyond began exchanging ideas at an unprecedented pace. Conferences, letters, and research papers flowed rapidly as physicists tried to understand and expand upon Schrödinger's work. This vibrant intellectual environment accelerated the development of quantum mechanics and created a new sense of shared purpose within the scientific community. Schrödinger's work during this time revealed his deep belief in the beauty of physical laws. He believed that a true theory of nature should not only be accurate, but also elegant and harmonious. Wave mechanics satisfied this personal ideal. It transformed a confusing set of experimental results into a coherent mathematical structure. In doing so, it reflected Schrödinger's belief that nature, at its deepest level, is governed by simple and beautiful principles, even if those principles appear strange to human intuition. The birth of wave mechanics did not just solve existing problems, it opened new doors. It provided the foundation for understanding chemical bonds, the behavior of solids, and the properties of semiconductors. Without wave mechanics, modern technology, as we know it, would not exist. Every time a smartphone works, a laser operates, or a computer processes information, it relies on principles that can be traced back to Schrödinger's revolutionary idea. By the end of this phase of his work, Schrödinger had permanently changed the course of science. What began as a quiet struggle with equations and ideas had become a global transformation in how reality itself was understood. The birth of wave mechanics was not just a scientific achievement. It was a moment when human thought stepped beyond the limits of classical imagination and entered a new era of understanding. As wave mechanics began to gain attention across the scientific world, its deeper meaning slowly started to unfold, not only for physicists, but for humanity's understanding of reality itself. The scientific community was no longer dealing with simple particles traveling along clear, predictable paths. Instead, they were confronting a world where probability, uncertainty, and wave-like behavior governed the very building blocks of matter. For many scientists, this was both exciting and uncomfortable. It required them to abandon long-held beliefs about certainty and determinism and accept a new vision of the universe. Schrödinger found himself at the center of this intellectual storm. Although naturally quiet and reflective, he was suddenly drawn into debates, discussions, and exchanges with the greatest scientific minds of his time. He communicated with physicists across Europe, responding to questions, criticisms, and ideas about his work. These conversations sharpened his thinking and helped clarify the meaning of wave mechanics. Unlike many revolutionary thinkers who resist criticism, Schrödinger welcomed it as a chance to deepen his understanding. One of the most powerful aspects of wave mechanics was how it tied together different branches of science. It did not remain limited to pure physics. Chemists quickly realized that it could explain how atoms bonded to form molecules. It clarified why certain chemical reactions happen and why molecules have specific shapes and energies. This link between physics and chemistry created a new scientific bridge that had never existed before. The invisible dance of electrons inside atoms could now be described with precise mathematical language. The philosophical impact of wave mechanics became just as important as its scientific success. Classical physics had encouraged the belief that the universe was like a perfectly designed clock, where everything moved according to fixed, predictable rules. Wave mechanics shattered this idea. It suggested that chance and probability were not just signs of human ignorance, but fundamental parts of nature itself. This deeply challenged the way people thought about free will, causality, and the nature of reality. Schrödinger himself felt conflicted about some of these implications. While he created the mathematical foundation of wave mechanics, he was never fully comfortable with the idea that reality was purely probabilistic. He hoped that one day, a deeper and more complete theory would restore a sense of clarity and determinism. This inner tension made his work even more human. He was not a cold, emotionless mathematician. He was a thinker struggling with the philosophical consequences of his own discoveries. As more experiments confirmed the predictions of wave mechanics, the scientific world began to fully accept it as a cornerstone of quantum theory. Electron diffraction experiments, spectral analysis of atoms, and studies of atomic structure all aligned with Schrödinger's predictions. Each successful experiment strengthened confidence in wave mechanics. What began as a bold theoretical idea had now become an essential part of scientific truth. The development of wave mechanics also influenced how science itself was practiced. It encouraged scientists to rely more heavily on abstract mathematics and less on direct physical visualization. Before this, most theories were built around pictures of tiny objects moving through space. Now, physicists were working with mathematical wave functions that could not be directly seen, only calculated. This shift marked the beginning of a new era of theoretical science, where mathematics became the primary language of reality. Schrödinger's growing fame brought him international recognition. Invitations arrived from universities and institutions around the world. His lectures attracted large audiences of students, physicists, and philosophers eager to hear directly from the man who had helped unlock the secrets of the atomic world. Despite this fame, he remained a humble and thoughtful person. He continued to see himself as a student of nature rather than a master of it. Wave mechanics also changed the future of technology in ways Schrödinger could never have fully imagined. It laid the groundwork for transistors, which later allowed the creation of computers. It made possible the development of lasers, medical imaging technologies, and modern electronic devices. Society slowly became shaped by discoveries that started as abstract equations on Schrödinger's desk. In this way, wave mechanics connected the invisible world of atoms with the everyday lives of billions of people. Another important consequence of wave mechanics was the way it encouraged collaboration between theory and experiment. Theoretical predictions made by wave mechanics inspired new experiments, and experimental results pushed theorists to refine their models. This dynamic relationship accelerated progress in science. Schrödinger's framework served as a bridge between pure thought and practical observation, proving that abstract ideas could have real, world power. As time passed, wave mechanics became fully integrated into the broader structure of quantum mechanics. Together with the contributions of other pioneers, it formed a coherent picture of how matter and energy behave at the smallest scales. Schrödinger's work was no longer seen as just one piece of a puzzle, but as a central pillar supporting an entirely new scientific world. The birth of wave mechanics had matured into the foundation of modern physics. Still, Schrödinger remained a thinker searching for deeper meaning. He continued to reflect on what wave mechanics said about the nature of truth, observation, and human understanding. He believed that science should not be separated from philosophy. For him, the equations were not just tools. They were windows into the mystery of existence. This perspective gave his scientific work a depth that went beyond technical achievement. The legacy of the birth of wave mechanics can be seen everywhere today. Every time scientists explore the behavior of tiny particles, every time engineers design advanced electronics, and every time doctors use sophisticated imaging tools, they are using principles rooted in Schrödinger's revolutionary idea. His work did not just explain the atomic world, it built the foundation for the technological civilization of the modern age. In the final analysis, the birth of wave mechanics represents one of humanity's greatest intellectual achievements. It shows how a single mind, driven by curiosity and guided by imagination and discipline, can change the way the entire world thinks. Schrödinger's journey from questioning student to scientific revolutionary proves that true discovery often begins with the courage to challenge what everyone else accepts as normal. What started as theoretical speculation evolved into a universal framework for understanding nature. The atomic world, once hidden behind mystery and contradiction, became a realm of mathematical beauty and conceptual depth. And at the heart of this transformation stood Erwin Schrödinger, whose vision gave humanity a new way to see reality. Schrödinger's equation is one of the most important scientific formulas in human history because it gives us a way to understand how matter behaves at the smallest possible scale. Before this equation existed, scientists were confused about how tiny particles, such as electrons, moved inside atoms. The rules of classical physics, which worked perfectly for large objects like planets and falling apples, completely failed when applied to the world of atoms. There was no clear mathematical tool to describe the strange and unpredictable behavior of particles at the quantum level. This is where Schrödinger's equation changed everything. At its core, Schrödinger's equation is a mathematical rule that describes how the wave function of a particle evolves over time. The wave function is not a physical wave like water waves in the ocean. Instead, it is a mathematical expression that carries information about a particle's possible positions and energies. Rather than telling us exactly where a particle is, it tells us the probability of finding it in a particular place. This was a huge shift in thinking because it replaced certainty with probability as a fundamental part of nature. Before this equation, scientists tried to imagine electrons as tiny balls orbiting the nucleus of an atom in neat, circular paths. However, experiments showed that this picture was too simple and incorrect. Electrons could behave in ways that seemed impossible under classical rules. Schrödinger's equation provided a new and accurate way to describe this behavior. It showed that electrons exist in clouds of probability rather than exact fixed paths. These clouds are called orbitals, and they represent the likely locations of electrons around the nucleus. One of the most powerful aspects of Schrödinger's equation is that it allows scientists to calculate the energy levels of electrons in atoms. These energy levels explain why atoms absorb and emit light in specific colors. When an electron jumps from one energy level to another, it absorbs or releases a precise amount of energy. This is the reason why we see unique spectral lines for different elements. This single application of the equation helped unlock the mysteries of chemistry, astronomy, and material science. The importance of Schrödinger's equation goes far beyond just describing electrons in atoms. It forms the foundation of the entire field of quantum mechanics. Once scientists had this equation, they could use it to study atoms, molecules, and even larger systems under certain conditions. It became the starting point for understanding chemical bonds, the structure of molecules, and the behavior of solid materials. Without this equation, modern chemistry would not exist in its current form. Another major reason this equation is so important is its role in the development of modern technology. Many of the technologies we depend on every day are built on principles that come directly from Schrödinger's equation. Semiconductors, which are the heart of computers and smartphones, rely on quantum behavior explained by this equation. Lasers, which are used in medicine, communication, and industry, also function based on principles described by it. Medical imaging tools and other advanced technologies depend on quantum-level understanding that began with this equation. Schrödinger's equation also changed how scientists think about reality itself. It introduced the idea that uncertainty is not just a limitation of human measurement, but a basic feature of the universe. The world at the quantum level does not allow perfect predictions, only probabilities. This was shocking at first because it challenged the idea that nature operates like a perfectly predictable machine. Instead, it revealed that reality is governed by chance and probability at its deepest level. The equation also brought together mathematics and physics in a powerful new way. It showed that complex physical behavior could be captured by elegant mathematical expressions. This inspired future generations of scientists to look for deeper mathematical patterns in nature. It transformed theoretical physics into a highly mathematical discipline, where equations became the main language for describing the universe. Even today, Schrödinger's equation remains essential. Scientists still use it to design new materials, study chemical reactions, and develop quantum computers. It is the starting point for understanding advanced topics like quantum tunneling, superposition, and entanglement. Every time researchers explore the quantum world, Schrödinger's equation is one of the first tools they reach for. In simple terms, Schrödinger's equation gave humanity a new lens through which to view the world. It took the invisible and made it understandable. It turned confusion into clarity and mystery into measurable prediction. It showed that the universe is not just made of solid objects following simple paths, but of waves, probabilities, and hidden structures that govern how everything behaves. In conclusion, Schrödinger's equation is important because it is the foundation of quantum mechanics, the bridge between mathematics and physical reality, and the key to much of modern science and technology. It changed how scientists understand nature, how engineers build technology, and how philosophers think about reality itself. It is not just an equation. It is one of the greatest ideas ever created in human history. The Schrödinger's cat thought experiment is one of the most famous illustrations of the strange and counterintuitive nature of quantum mechanics. It was proposed by Erwin Schrödinger in 1935, not as a serious experiment to be performed in a laboratory, but as a way to demonstrate the problems and paradoxes that arise when the rules of quantum mechanics are applied to everyday objects. Schrödinger wanted to show that, although quantum theory works incredibly well for tiny particles like electrons and atoms, its principles can seem absurd when we try to imagine them at the scale of ordinary life. To understand the thought experiment, it is important to remember what Schrödinger had already discovered with wave mechanics. In quantum physics, particles such as electrons do not have definite positions or states until they are measured. Instead, they exist in a superposition, a combination of all possible states at once. For example, an electron could be in two different energy levels simultaneously until an observation forces it to choose one. This concept is extremely difficult to grasp because it contradicts our everyday experience, where objects always appear to have definite properties. Schrödinger wanted to take this idea of superposition and apply it to a more familiar, real-world scenario in order to highlight the apparent absurdity. He imagined a cat placed inside a sealed box with a small, carefully controlled device. This device contains a tiny amount of radioactive material, a Geiger counter, and a mechanism that releases poison if the radioactive atom decays. Quantum theory tells us that the radioactive atom is in a superposition of decayed and not decayed until it is observed. Therefore, according to quantum mechanics, the mechanism is simultaneously triggered and not triggered, and as a result, the cat is simultaneously alive and dead until someone opens the box and looks inside. The thought experiment was designed to illustrate a paradox. Schrödinger wanted to show that the direct application of quantum mechanics to large-scale objects leads to results that are nonsensical from a classical perspective. No one would expect a cat to be alive and dead at the same time in reality, yet the rules of quantum theory, taken literally, suggest exactly that. This apparent contradiction forced scientists to think more deeply about the meaning of measurement and observation in quantum mechanics. One of the key insights from Schrödinger's cat is the role of the observer in quantum theory. In the quantum world, the act of measurement is not passive. Observing a system forces it to collapse from a superposition of multiple possibilities into a single, definite outcome. Until that observation occurs, the system exists in all of its possible states simultaneously. Schrödinger used the cat as a way to dramatize how strange this idea is when applied to something we can see, touch, and understand directly. It challenges the intuitive notion that objects have inherent, independent reality. The thought experiment also highlights the difference between quantum and classical scales. While superposition and wave functions accurately describe particles like electrons, applying the same rules to a cat or other macroscopic object exposes the limits of our understanding. Schrödinger's goal was not to suggest that cats literally exist in two states, but to provoke a conversation about the boundary between the microscopic world, governed by quantum laws, and the macroscopic world, governed by classical laws. Philosophers and scientists have debated Schrödinger's cat for decades. Some interpret it as evidence that reality itself is fundamentally probabilistic, and that objects only gain definite properties when observed. Others suggest that there are hidden variables or mechanisms we do not yet understand that would remove the paradox entirely. The thought experiment has inspired numerous interpretations of quantum mechanics, including the Copenhagen interpretation, which emphasizes the importance of measurement, and the many worlds interpretation, which suggests that all possible outcomes actually occur in separate, branching universes. Beyond philosophy, Schrödinger's cat has had a profound impact on science and culture. It has become a symbol for the mysteries of quantum mechanics and a teaching tool for students learning about the strange behaviors of particles. It illustrates the idea that the quantum world does not obey the rules of common sense, and it challenges scientists to think creatively about the nature of reality. The paradox of the cat encourages a deeper exploration of questions such as, what does it mean for something to exist? How does observation influence reality? And how can we reconcile the microscopic and macroscopic worlds? Interestingly, advances in modern physics have brought scientists closer to experimentally testing ideas related to Schrödinger's cat. Researchers have been able to create superpositions in small systems, such as molecules, ions, and photons, where states exist simultaneously in ways that resemble the principle illustrated by the cat. These experiments demonstrate that superposition is not just a theoretical idea. It is a real phenomenon in the quantum world. However, as Schrödinger predicted, maintaining superposition in large objects remains practically impossible because interactions with the environment, known as decoherence, force systems into definite states almost instantly. The importance of Schrödinger's cat extends beyond physics. It has influenced computer science, particularly in the development of quantum computing. In a quantum computer, qubits can exist in superpositions of 0 and 1, similar to how the cat can be alive and dead simultaneously. This property allows quantum computers to perform calculations much faster than classical computers for certain tasks. In this way, the thought experiment has practical implications for future technology, even though it began as a philosophical illustration. Schrödinger's cat also captures the imagination of the general public because it makes abstract quantum concepts more relatable. By using a familiar object, a cat Schrödinger transformed an obscure scientific problem into a story that anyone can understand. The image of a cat being both alive and dead at the same time has become iconic, appearing in books, films, and discussions about science, philosophy, and reality itself. It serves as a reminder that science can challenge our deepest intuitions and force us to reconsider what we think we know about the world. In conclusion, Schrödinger's cat is more than a quirky idea. It is a profound illustration of the strangeness and depth of quantum mechanics. It shows how the principles of superposition and measurement challenge classical notions of reality and force scientists to think beyond everyday experience. While no one expects a real cat to be alive and dead simultaneously, the thought experiment remains a powerful tool for understanding the conceptual and philosophical implications of quantum theory. It continues to inspire scientists, philosophers, and curious minds around the world to explore the limits of knowledge and the mysteries of the universe, just as Schrödinger intended. Erwin Schrödinger played a central and transformative role in shaping quantum theory, one of the most important scientific revolutions of the 20th century. While many scientists contributed to the development of quantum mechanics, Schrödinger's unique combination of mathematical skill, philosophical insight, and creative imagination allowed him to provide a clear and coherent framework that would become essential for understanding the microscopic world. His contributions not only advanced the field of physics, but also influenced chemistry, technology, and our very understanding of reality. Schrödinger entered the world of quantum mechanics during a period of profound uncertainty in physics. By the early 1920s, classical physics had already shown its limitations. Phenomena such as blackbody radiation, the photoelectric effect, and atomic spectra could not be explained by Newtonian mechanics or Maxwell's equations. Physicists had developed partial solutions. Planck's quantization of energy, Einstein's explanation of light, as photons, and Bohr's model of the atom. However, these ideas were fragmented and lacked a unifying theoretical foundation. Schrödinger recognized that a more comprehensive framework was needed, one that could describe the behavior of particles in a way that was both mathematically precise and conceptually consistent. Schrödinger's major contribution to quantum theory came in the form of wave mechanics. In 1926, he formulated the Schrödinger equation, a revolutionary mathematical tool that described how the quantum state of a system evolves over time. This equation provided a precise way to calculate the probabilities of finding particles in various positions and energy states. Unlike earlier models, which relied on classical trajectories or discrete assumptions, the Schrödinger equation captured the inherently wave-like nature of matter. It offered a consistent framework for understanding phenomena ranging from electron orbitals to atomic spectra. One of the most significant aspects of Schrödinger's work was that it connected abstract mathematics with physical reality. The Schrödinger equation describes a particle's wave function, a complex mathematical entity that encodes all the information about a quantum system. The square of the wave function gives the probability distribution of the particle's position or momentum. By providing this link between mathematical description and measurable outcomes, Schrödinger made quantum mechanics both practical and predictive. Scientists could now calculate atomic behavior with remarkable accuracy and test these predictions in experiments. Schrödinger's approach also helped bridge a conceptual gap in quantum theory. At the time, Werner Heisenberg had developed matrix mechanics, a different mathematical formulation of quantum mechanics. While matrix mechanics was powerful, it was highly abstract and difficult to visualize. Schrödinger's wave mechanics offered an alternative that was more intuitive. By describing particles as waves and providing a continuous representation of their behavior, he allowed scientists to see quantum processes in a more understandable way. Eventually, it was proven that wave mechanics and matrix mechanics were mathematically equivalent, demonstrating the robustness of the quantum framework. Beyond the Schrödinger equation itself, he contributed philosophical insight to quantum theory. Schrödinger was deeply concerned with the interpretation of quantum mechanics and the meaning of its predictions. His famous thought experiment, Schrödinger's cat, highlighted the apparent paradoxes of quantum superposition and measurement. He questioned whether the probabilistic nature of quantum mechanics truly described reality or if it was a temporary, incomplete theory. These reflections forced physicists to think carefully about what quantum mechanics says about the nature of existence, observation, and determinism. In this way, Schrödinger shaped not only the technical development of quantum theory, but also its conceptual foundations. Another important contribution of Schrödinger was his influence on atomic and molecular theory. By solving the Schrödinger equation for the hydrogen atom, he was able to calculate the allowed energy levels of electrons with unprecedented accuracy. This explained why atoms emitted or absorbed light at specific frequencies and provided a precise theoretical foundation for spectroscopy. Later, his work was extended to multi-electron atoms and molecules, laying the groundwork for quantum chemistry. Today, our understanding of chemical bonding, molecular structure, and reaction dynamics relies heavily on the principles he developed. Schrödinger's role in shaping quantum theory was also characterized by collaboration and engagement with other leading physicists of his time. He interacted with Albert Einstein, Niels Bohr, Max Born, and many others, exchanging ideas and refining concepts. These interactions helped clarify the mathematical and philosophical aspects of quantum mechanics. Schrödinger's voice was influential in debates about interpretation, and his insistence on conceptual clarity helped prevent the field from becoming purely formal and disconnected from reality. Importantly, Schrödinger's contributions had long-term practical implications. The tools and concepts he developed became essential for modern physics and technology. Wave mechanics enabled the design of semiconductors, lasers, superconductors, and other quantum-based devices. It provided the theoretical foundation for quantum information science and quantum computing, fields that are at the cutting edge of research today. His work showed that abstract mathematics could lead to tangible applications that transform society, proving the profound importance of theoretical physics. Schrödinger's influence also extended to education and communication in physics. His ability to explain complex quantum concepts in intuitive ways made him a remarkable teacher and mentor. Through lectures, papers, and books, he trained a generation of scientists to think in terms of wave mechanics and quantum probability. His textbook, Principles of Quantum Mechanics, became a standard reference for decades, shaping how students learned and understood the subject. By combining mathematical rigor with conceptual clarity, he made quantum mechanics accessible to both researchers and students. Finally, Schrödinger's role in shaping quantum theory cannot be separated from his broader intellectual vision. He believed that science should not only describe facts, but also strive to reveal deeper truths about the universe. His work in quantum mechanics reflected this philosophy, as he sought both precise equations and meaningful interpretations. He challenged assumptions, questioned conventional wisdom, and encouraged others to think critically about the nature of reality. In doing so, he elevated quantum mechanics from a technical discipline to a field that addresses fundamental questions about existence itself. In conclusion, Erwin Schrödinger's role in shaping quantum theory was multifaceted and transformative. He provided the mathematical tools of wave mechanics, offered deep conceptual insights, solved critical problems in atomic and molecular physics, and influenced the development of modern technology. He bridged abstract mathematics and physical reality, making quantum theory both practical and understandable. Through his equations, thought experiments, writings, and teaching, he guided the scientific community toward a coherent understanding of the microscopic world. Without Schrödinger, quantum mechanics might have remained fragmented, confusing, and incomplete. His contributions remain central to our understanding of nature, ensuring that his legacy continues to shape science, technology, and philosophy to this day. Erwin Schrödinger's contributions to physics and science as a whole earned him tremendous recognition during his lifetime and secured his place as one of the most influential scientists in history. His groundbreaking work in quantum mechanics, particularly the formulation of wave mechanics and the Schrödinger equation, revolutionized our understanding of the microscopic world. These achievements brought him not only national but also international acclaim, establishing him as a central figure in the development of modern physics. One of the highest honors Schrödinger received was the Nobel Prize in Physics in 1933, which he shared with the Austrian physicist Paul Dirac. This award recognized his extraordinary contribution to the development of wave mechanics, an essential component of quantum theory. Receiving the Nobel Prize not only honored his scientific accomplishments, but also validated the revolutionary nature of his work. At the time, quantum mechanics was still a relatively new and controversial field, and this recognition affirmed its importance and legitimacy within the global scientific community. The Nobel Prize cemented Schrödinger's reputation as one of the leading physicists of the 20th century. Beyond the Nobel Prize, Schrödinger's work earned him a multitude of accolades, invitations, and positions at prestigious institutions around the world. His reputation as a brilliant thinker and an innovative scientist led to teaching and research appointments in multiple countries, including Germany, Switzerland, Austria, and later Ireland. In 1939, he accepted a position at the University of Dublin, where he became the director of the School for Theoretical Physics. This appointment allowed him to influence a new generation of scientists while continuing his research in an environment supportive of intellectual freedom. Through his teaching and mentorship, Schrödinger extended his influence far beyond his own research, shaping the thinking of countless physicists and mathematicians. Schrödinger's global influence was not limited to formal awards or positions. His research papers, particularly those on wave mechanics and quantum theory, were widely circulated and studied internationally. Scientists across Europe, the Americas, and Asia engaged with his ideas, applying them to problems in atomic physics, chemistry, and solid-state physics. The clarity and elegance of his mathematical formulations made his work accessible and inspiring, even to those not directly specializing in quantum mechanics. His influence was particularly significant in bridging the gap between abstract mathematics and practical physical interpretation, which helped quantum theory gain acceptance across the scientific world. Another aspect of Schrödinger's recognition lies in the impact of his philosophical contributions to science. His thought experiments, such as Schrödinger's cat, sparked discussions not only among physicists, but also among philosophers and thinkers concerned with the nature of reality. This unique ability to connect rigorous scientific work with deeper philosophical questions amplified his influence, demonstrating that physics could inform our understanding of existence itself. As a result, Schrödinger became not just a celebrated scientist, but also a respected intellectual figure whose ideas transcended the laboratory. Internationally, Schrödinger was invited to participate in conferences, symposiums, and lectures around the world. These platforms allowed him to interact with other leading scientists, exchange ideas, and inspire collaboration. His clear and thoughtful presentation of complex concepts made him a highly respected speaker, and his ideas spread rapidly through the scientific community. Even after moving to Ireland, Schrödinger maintained active correspondence with scientists in Austria, Germany, and other countries, ensuring that his contributions continued to shape the evolving landscape of quantum theory. In addition to influencing scientists, Schrödinger's work left a lasting mark on education. His textbooks and publications became standard references for students and researchers alike. In particular, his book Principles of Quantum Mechanics became one of the most widely used and cited texts in the field. It provided not only rigorous mathematical treatment, but also conceptual explanations that helped learners understand the meaning and significance of quantum phenomena. Through this educational influence, Schrödinger's ideas reached generations of physicists and chemists, extending his impact well beyond his immediate research. Schrödinger's recognition also reflected the broader cultural and intellectual significance of his work. By transforming our understanding of the atomic world, he contributed to a fundamental shift in how humanity perceives reality. His research challenged classical assumptions and inspired new philosophical and scientific debates about determinism, probability, and the nature of observation. This influence reached beyond the boundaries of physics, affecting other disciplines such as chemistry, philosophy, and even computer science. Schrödinger's ideas provided the foundation for emerging technologies, including semiconductors, lasers, and quantum computing, further amplifying his global impact. Despite his fame, Schrödinger remained a humble and thoughtful figure. He valued the pursuit of knowledge over personal recognition, and he often emphasized the importance of conceptual clarity and philosophical reflection in scientific work. This integrity and intellectual honesty earned him respect from colleagues worldwide and added depth to his global influence. He was not just admired for his discoveries, but also for his approach to science, rigorous, imaginative, and deeply reflective. In recognition of his lasting contributions, Schrödinger's name has been immortalized in multiple ways. The term Schrödinger's equation is universally recognized in physics, and the thought experiment Schrödinger's cat has become a symbol of the strange and fascinating world of quantum mechanics. These concepts appear not only in textbooks and scientific literature, but also in popular culture, reflecting the profound reach of his ideas. His work continues to inspire scientists, educators, and curious minds around the globe, decades after his death. In conclusion, Erwin Schrödinger's awards, recognition, and global influence reflect the extraordinary significance of his contributions to science. The Nobel Prize, prestigious academic positions, international collaborations, influential publications, and philosophical insights all demonstrate the magnitude of his impact. Through his research, teaching, and writings, he shaped the development of quantum theory, influenced generations of scientists, and contributed to technological and philosophical advancements that continue to shape the modern world. Schrödinger's life and work remain a testament to the power of curiosity, imagination, and intellectual rigor, establishing him as one of the most important figures in the history of science. Erwin Schrödinger's contributions to science did not end with his lifetime. His legacy continues to resonate deeply in modern physics, chemistry, technology, and even philosophy. The ideas and frameworks he developed, most notably wave mechanics and the Schrödinger equation, have become foundational pillars of quantum theory, guiding scientific research and technological innovation for nearly a century. Schrödinger's influence extends far beyond his own discoveries, shaping the way scientists think about the universe and how we interact with the microscopic world. One of the most enduring aspects of Schrödinger's legacy is the Schrödinger equation, which remains central to quantum mechanics. This equation allows scientists to predict the behavior of particles, atoms, and molecules with extraordinary accuracy. It serves as the mathematical foundation for understanding phenomena such as chemical bonding, atomic spectra, electron configurations, and the behavior of solids and liquids. Without Schrödinger's equation, modern quantum mechanics would lack its coherence and predictive power, making much of contemporary physics and chemistry impossible. Researchers today still rely on this equation to explore complex systems, from the tiniest subatomic particles to advanced materials with novel properties. Schrödinger's work also laid the groundwork for quantum chemistry, an entire field that studies the behavior of molecules and their interactions at the quantum level. By applying the principles of wave mechanics to atoms and molecules, scientists are able to understand the nature of chemical bonds, predict molecular structures, and explain chemical reactions with remarkable precision. His contributions enable the development of new drugs, materials, and chemical processes. In this way, Schrödinger's work has had a direct impact on medicine, industry, and everyday life, demonstrating that theoretical physics can lead to tangible, practical benefits. Another significant part of his legacy is the concept of superposition and its philosophical and technological implications. Schrödinger's famous thought experiment, Schrödinger's cat, continues to be a symbol of quantum mechanics' strange and counterintuitive nature. It challenges classical ideas of reality, determinism, and observation, forcing scientists and philosophers to reconsider how the universe behaves at its most fundamental level. This thought experiment remains a central teaching tool in physics education, helping students and researchers alike to grapple with the conceptual challenges of quantum mechanics. Schrödinger's influence is particularly evident in modern technology. His work underpins the operation of semiconductors, which are essential components in computers, smartphones, and other electronic devices. Lasers, which have countless applications in medicine, communication, and manufacturing, are also based on principles that emerge from quantum mechanics. More recently, quantum computing, a rapidly developing field, relies heavily on the idea of superposition and wave functions, both of which are rooted in Schrödinger's discoveries. Without his contributions, these transformative technologies would not exist, highlighting the profound practical legacy of his work. In addition to his scientific achievements, Schrödinger influenced scientific thought and education. His textbooks and publications, particularly Principles of Quantum Mechanics, remain classic references for understanding the principles and mathematics of quantum theory. He had a unique ability to explain highly abstract concepts with clarity, balancing rigorous mathematics with conceptual insight. Generations of scientists, engineers, and educators have been trained using his methods, and his approach continues to inspire clear and thoughtful teaching in physics and related fields. Schrödinger's impact also extends to interdisciplinary research. His interest in the philosophical and conceptual aspects of science influenced areas such as biology, cognitive science, and information theory. Notably, his book What is Life, published in 1944, inspired future biologists and geneticists, including Francis Crick and James Watson, who discovered the structure of DNA. By connecting physics with questions about living systems, Schrödinger demonstrated the power of interdisciplinary thinking and the broader relevance of scientific principles beyond a single field. This aspect of his legacy continues to encourage scientists to approach complex problems in an integrated, holistic manner. Moreover, Schrödinger's legacy lies in the culture of scientific inquiry and imagination that he exemplified. He approached physics not just as a technical discipline, but as a pursuit of understanding the deepest principles of nature. He combined rigorous analysis with creative thinking, intuition, and philosophical reflection. This approach has influenced generations of researchers who seek not only to calculate results, but also to grasp the underlying meaning of their discoveries. Schrödinger's example reminds the scientific community that imagination and curiosity are as essential as technical skill in advancing human knowledge. Another lasting contribution is the global recognition of quantum mechanics as a complete framework for understanding nature at the microscopic level. Schrödinger's wave mechanics helped unify a fragmented set of theories into a coherent structure. By demonstrating the equivalence of wave mechanics with matrix mechanics, he showed that different mathematical approaches could describe the same physical reality, thereby reinforcing the robustness and universality of quantum theory. This unification paved the way for further breakthroughs in particle physics, condensed matter physics, and cosmology, highlighting the lasting influence of his work on the direction of modern science. Finally, Schrödinger's legacy can be seen in the continued intellectual curiosity and philosophical reflection that his work inspires. His emphasis on questioning assumptions, exploring conceptual paradoxes, and seeking deeper understanding continues to resonate in scientific research and education. The questions he raised about observation, reality, and probability remain central to ongoing debates in the foundations of quantum mechanics, ensuring that his ideas remain relevant to both theoretical research and philosophical inquiry. In conclusion, Erwin Schrödinger's lasting legacy in modern science is vast and multifaceted. His wave mechanics and Schrödinger equation transformed quantum theory into a powerful, predictive, and conceptually rich framework. His work enabled advances in chemistry, technology, medicine, and interdisciplinary research, while also inspiring philosophical inquiry and intellectual curiosity. Through his teaching, writings, and thought experiments, he shaped generations of scientists and thinkers. Today, his influence is felt not only in laboratories and classrooms, but also in the technologies that define modern life. Schrödinger's legacy is a testament to the enduring power of imagination, rigor, and curiosity, ensuring that his contributions will continue to shape science and human understanding for generations to come.